This is my lab 2 on projectile motion. This is my table of contents. The purpose of this lab was to analyze how air resistance or drag affects projectile motion. To do this, we use two modeling tools, Tracker and GlowScript. Tracker is a video analysis software that can give us position and velocity data, and GlowScript is a computational model that can predict ideal projectile motion. This lab is based on the fundamental principles of Newton's second law and the kinematic equations for position and velocity. Throughout this presentation, I will refer to the three formulas shown, the position update formula, the velocity update formula, and Newton's second law. Our prediction is that the computational model that incorporates air resistance will more closely match the actual experimental data, therefore showing that air resistance does affect projectile motion. However, as you will later see, the experimental data was actually closer to the model without air resistance, and that was due to various sources of air, which I will also explain later. For this lab, the system is a crumpled piece of paper, and the surroundings include air and the earth. We will make the assumption that the crumpled paper has a uniform mass because we didn't have access to a perfectly ideal sphere. We're also going to use Newton's second law, which allows us to describe the motion of any object in terms of the forces acting upon it. In this lab, the two primary forces that we're going to consider are the force of gravity and the force of drag. As shown in the slides, the force of drag is equal to negative bv squared, and by definition, it acts in the direction opposite to the object's motion. Our initial conditions are in the y direction, we have both the force of gravity and the y component of the drag force, and in the x direction, we only have the x component of drag force. A free body diagram shown is one on the left. The free body diagram on the right is what it looks like at the end of the motion, where drag is pointing upwards. Shown in the slides is my tracker analysis, and as you can see, I set the meter stick as our reference length, and the magenta axes are right below where I started the object. I chose to start tracking a few frames after the ball was released to minimize the amount of initial force, to minimize the influence of the initial force applied to the object. And from tracker, as you can see, I got x values, y values, and velocity and acceleration data. Now for the computational data, since the goal of our lab is to analyze how the force of drag affects motion, we're going to create two models, one that includes drag and one that does not. When we compare these models to our actual experimental data, then we can see which is more accurate. So in my code, the initial position is taken from tracker at time 0, and the initial velocity is calculated using the first two data points. And then we're going to set the frame rate 0.01 seconds as our time step. Additionally, we define both the forces of gravity and drag. So for the first model, we can eliminate drag by simply setting the proportionality constant b to 0. In the top right image, the cyan arrow represents our relative direction and force of gravity, and the magenta arrow is velocity. Now, for the second model, we want to account for the force of drag. To do this, we simply give a value to our proportionality constant b. And we experimentally found this using the sum of the forces in the y direction and the acceleration in the y direction. You can calculate acceleration in the y direction by using the first three data points, calculating for velocity and then acceleration. And the b value I got was negative 0.05. Now, in the top right image, the orange arrow represents the relative direction and force of drag. Comparing our data. So the graph is read from right to left because we toss our object from right to left. And a similarity you can note is that there's a gap between the red and the yellow line. And this gap, it slowly increases as you go from right to left because as velocity increases, so does the force of drag. So as the force of drag increases, the yellow line will start to dip more and more. Despite the differences, all the graphs share a relative general shape, and that's because they all model projectile motion. Some sources of error. So the first source of error is that if our hand shakes when we take the video, then our axes could shift upwards, and this means that every y value we select will be larger than it's supposed to be. Another source of error is human error in tracker. Since we manually select the ball each time, it's impossible to click the exact perfect spot. Additionally, the way we calculate for the proportionality constant is by using only the first 2 points, which is not perfect, but it is also the most efficient. For the what does it mean question, only the model with drag will predict terminal velocity because at a certain point, the downward force of gravity is exactly balanced by the drag force, causing the object to fall at a constant speed. So as shown in the right, the velocity is starting to reach an asymptote and it's starting to level out. And the graph on the left is the model without drag, and as you can see, it's always keeping that linear shape, and it will never level off or reach a constant speed. For the what if question, if the object were initially thrown straight upward with the same initial speed, it would take more time to reach the ground. Because if you think about it, if it's thrown straight up, then it has a larger y velocity. So with a larger y velocity, it's going to reach a higher maximum vertical position, and if it goes higher, then it's going to take longer to reach the ground. So because in a toss motion that there's less velocity in the horizontal motion, that means it goes less high and it's going to reach the ground first. Thank you.